So for instance, if you have a car crash on the highway, obviously those cars, when they're colliding, are not their own little isolated bubble in the world. They have friction from the road, they have air resistance, other things, but that friction and air resistance is tiny compared to the violent force they will have with each other, that they will exert on each other. So momentum conservation is actually very useful in a broad variety of situations. It doesn't just apply when you can perfectly isolate from the outside world, okay? So there are a couple homework problems where you might question, is this really isolated from the outside world? Well, we're kind of playing a little bit, this is the game of physics where you say it's not the perfect conditions, but it's close enough for our purposes, okay? Okay. So the next thing to do to move forward is to find out how to incorporate energy into this. Just because we've changed gears and haven't talked about energy for a lecture or two, energy is still a concern for us. And so now what we're going to do is take a look at these together. So look at a bunch of systems. Is the momentum conserved? Is the energy conserved? Are they both conserved or neither conserved? So let's go ahead and do that. So let me remind you the conditions under which these things are conserved. So when the net external force is basically can be zero or approximated as such, momentum of a system is conserved. So the main question you're asking yourself when you're trying to figure out whether momentum conservation should be used is asking yourself about internal forces versus external forces. That's your main question. If you're trying to figure out how to cordon off your system, you're trying to cordon it off so there isn't this massive external force, because a massive external force is going to change the momentum. So one thing you might do is say, okay, I can't use momentum conservation because there's this big net external force. Another thing is to ask, hey, what's causing that? Let's invite it into our system, because then one person's external becomes another person's internal, right? Let's invite the thing that's this big external force, make it part of our system. Then it's internal. Then we can use momentum conservation. So that's always what you're trying to do when you're trying to figure out how to conserve momentum. You're asking yourself about internal and external forces. You're trying to get all the big forces inside, and all the small or negligible forces can be outside. Okay? So let me do a little Venn diagram here. Just characterizing forces. Okay? So of course, there was no distinction of forces. Forces were forces when we did the force method. You just got to include them all. But now we're recognizing that we might want to put forces into subgroups, and one of the ones we're interested in is internal versus external. You guys know what a Venn diagram is? If they overlap, then they have a common subset. Okay? These don't, though, right? A force can't be internal or external, so they don't have any common ground. It's either internal to the system or it's external, right? If we can get all the forces into the internal category, then we can use momentum conservation. If we have some significant external forces, then momentum conservation will not apply, okay? So that's momentum conservation. Let's go over to mechanical energy conservation. That was a completely different story. Mechanical energy, which is Ke plus Pe, is conserved only when you don't have these pesky forces called non-conservative forces. So only if the non-conservative forces do no work can we be guaranteed that the Ke plus Pe is conserved. Ke plus Pe is E, mechanical energy. So we had these pesky forces. Friction was one of them. It took kinetic energy and sent it to heat. Another one was an applied force, which can take chemical energy and bring it into the system as mechanical energy. These pesky forces that cross the macro-micro barrier, and therefore they are annoying to deal with. It would be nice in many problems if they weren't there. Non-conservative work was zero, so we could just say Ke plus Pe is conserved and go from there. So the question you're asking yourself, and hopefully you're asking yourself this right now when you're doing homework number 7, is do you have any of these or not? So do you have only conservative forces like gravity, or do you have non-conservative forces that you have to contend with like friction? All right, so let's add to our Venn diagram. Those are two other ways to categorize forces. So you can categorize them as conservative or non-conservative. And of course, those two don't overlap with each other. You're one or the other. You can't be both simultaneously. But of course, they do have some overlap with the other categories. So we have 4 regions of overlap here. And those 4 regions of overlap are going to determine if one or both things are conserved. So let's take a look at each of the 4. If you have internal forces only, so no net external force, is momentum conserved? Yes, it is. Okay? So this momentum is conserved, and this momentum is conserved. If there are significant external forces, it's not. So that's the top and bottom, the internal versus external. All right. Let's take a look at conservative versus non-conservative. So if you have only conservative forces, like gravity, for instance, is mechanical energy conserved? Yes. So over here we have energy is conserved, mechanical energy, and over here we have it as well. Over here it's not. Those are all the permutations. So what I'm going to do now is simply start proposing a number of different systems, and we're going to evaluate, is momentum conserved? Is mechanical energy conserved? Are they both conserved? Is one of them conserved? Is neither conserved? If you understand this bunch, if you can look at these scenarios that I'm about to give you and be able to identify which conservation is, if either, is applicable, you understand a huge portion of what Physics 1 is all about, okay? So these are the 2 major conservations in our class. I think there's going to be one more, angular momentum. But these are the 2 major conservations. And remember, if you understand momentum and energy are just built up off the backs of forces, right? Newton's 3rd law leads to momentum conservation, and Newton's 2nd law, F net equals ma, we used in the derivation of the work energy theorem. So momentum and energy are like higher level, higher plane thinking of what's going on with Newton's laws, okay? So let's do this. Let's propose a number of different scenarios. We'll see which conservations would be applicable. I'm going to put the scenario in the first column. I'm going to ask, is momentum conserved for this system? I'm going to ask, is mechanical energy conserved for the system? And I'm going to leave a column for comments so I can discuss the system in more detail. Now let's just propose a bunch of these. So if I give you either these or some variants on the exam, you'll be able to, if you understand thoroughly what this chart is kind of getting at, you'll be able to identify what conservations are appropriate. The first one, I'm going to have a frictionless horizontal, so mu k is 0. It's a frictionless surface. I'm going to have two objects colliding. A collides with B. Doesn't matter if B is at rest or not. And my system is going to be identified as the A and B together. So I put a little bubble around those two. All right. So, first of all, is the momentum of the A and B system conserved? Yes, it is. We've done our best as we can do in the real world, to isolate A and B from their outside environment. It's on a flat, frictionless surface. So the major force involved, which is their collision force, is internal, and that's fine. Internal force trades momentum between the things, not changes the total. So here, the internal force is just fine. There's no net external force. Okay? Now here's the tricky thing. Because we don't know anything about the force, the collision force. There are many different ways in which these things could collide. So we can't necessarily say that that internal force is conservative or non-conservative. As long as it's internal, momentum conservation doesn't care. Okay? I like to think of momentum, that's like the Las Vegas conservation, right? What happens in Vegas stays in Vegas, right? As long as it's inside. Have you heard this saying? Okay? But just because it's internal only and momentum is happy doesn't mean that energy isn't concerned about that. It's like your mom saying, I know that saying about Vegas, but you can tell me what happened, right? Was that conservative or non-conservative what happened there, okay? So it could be either one. So we need to examine both possibilities. It could be that, yes, it's conserved because it's internal conservative force, or it could be no, because it's an internal non-conservative. So these get names. If it's an internal conservative force, you call it an elastic collision. And if it's an internal non-conservative force, you call it an inelastic collision. Have you guys done the momentum lab yet? This week? Okay, so some of you have, some of you haven't. Okay, so this hopefully will fill in what you did or can help inform what you did. So let's take a look. So what would be an example of an internal conservative force? One of the ways that you can imagine that two things collide, I think this is what you do in lab, maybe one of them just has like a spring on it or a rubber band or something. Rubber band. So a rubber band has a type of potential energy. It's not gravitational potential energy, but it's spring potential energy. You know, when you compress a spring, you can't just walk away and expect it to be like that, right? As soon as you let go, it springs back. So it stores energy for you, and then it gives it back to you. That's the perfect example of potential energy, right? Potential energy is energy that you can store and then get back, right? So what happens during these collisions is that the kinetic energy of the system, which is initial, that's all the energy is in that form before they hit each other, it goes into spring potential energy during the collision, but then those springs will unleash that energy back to the objects, and you will find it back in the objects afterwards. It doesn't literally need to be a spring. It could be anything that's basically springy, right? So a rubber band basically functions the same way, right? You stretch a rubber band, it springs back. It gives the energy that you put into it back. Another thing could be is that it's not even a rubber band, it's just a squishy, kind of rubbery surface, right? So if a surface is elastic, what that means is that it compresses, stores that energy, and then it says, here you go, take it back, okay? So it could, for instance, be two rubber balls colliding. That would be roughly elastic. So what you find is there that you have the internal collision force is conservative. It might store the energy for you during the collision and then just hand it right back to you, and it's all there afterwards. So for an elastic collision, if you count up the kinetic energy of the system initially, and you count it up at the end, it's all still there. Okay? I think that's part of your lab, is to verify that the energy is all there. You may not do it directly, but you do it in terms of some equations, which I don't want to get into, which basically come from the assumption that kinetic energy is conserved, and you're checking to see if the velocities agree. So one of the things you can do to check if you have one of these is tally up your initial kinetic energy of both objects, and then ask, when you tally it up again at the end, you get the same thing. If it's all there, you had the elastic collision. By the way, this is a very easy thing to compute, because remember, in kinetic energy, this is total speed. That's the only ingredient you need. And energy is not a vector, so you just count up the total speed, 1/2 mv squared. It's not like momentum where you have to have components. Okay? Remember, energy is not a vector. Are there any questions on the elastic collision? Yeah. Sorry?
The okay, the F internal.
Yeah, that's yeah. So internal forces are perfectly fine. They don't ruin your momentum conservation. Any other questions? Okay, so let's turn to the other possibility. You have an internal non-conservative force. So whatever way you're colliding, it's resulting in not just storage of energy, but a loss of energy. So I think what you do in your lab is you switch out so that instead of hitting rubber bands with each other, you instead have a needle burrowing into a clay pot. Yes? Is that what they still do? Okay? So you can imagine a needle burrowing into a clay pot. The clay is going to move out of the way, and it's not going to push the needle back out, right? So what's happened to that energy instead? It's gotten dissipated to heat, right? A needle burrowing through clay is going to dissipate energy to heat. So what you have is that the kinetic energy of the system, which is here initially, goes partially into heat, and you're generally not going to get it all back. You usually don't stop dead. You still have some kinetic energy left at the end, but you definitely lost some to the environment. So you dissipated energy to the environment from within. So something happened inside the system that made the system lose energy to the outside world. So here, when you count it up, the kinetic energy of the system is going to be larger at the beginning, and it's not all there at the end. I should mention as well that the inelastic category gets broken up into two subgroups as well. There is the somewhat and completely inelastic. The completely inelastic is something where you have lost so much energy to the environment that you cannot lose any more. Now that doesn't mean you stop dead. You can't stop dead because these are all momentum conserving collisions. So that means that if there's momentum in the system beforehand, there has to be momentum afterwards. And if you stop dead, there wouldn't be any. So the question then is, how do you lose as much kinetic energy as you can while still living up to your momentum conservation obligations? Well, it turns out that you don't even have enough energy left to bounce off. So what happens is that when the two surfaces deform, that becomes a permanent deformation. They don't spring back at all. And so they don't even have enough energy left to part ways. So the way that you know you have one of these is that the objects stick together and move together afterwards. So you know you have one of these. This is maximum kinetic energy loss when the final speeds or final velocities of your objects are the same. So if you ever see a collision where the two things don't bounce, but they are just go off together at the end, you know immediately you have one of these. You know immediately you've lost kinetic energy in your system. In fact, you've lost as much as you possibly can under the umbrella of momentum conservation. They don't even have enough energy left to bounce off. All the energy has been gone into permanent deformation, out to the environment as heat. So the two things kind of move together and just move in whatever fashion is needed to obey to fulfill their momentum conservation obligations. Okay? So remember that these two imply one in each other. Those are easy to spot. Anytime you see a collision where two things end up going together at the end, no way that kinetic energy is all there. The tricky one is to realize that the opposite is not true. Just because they don't stick together doesn't mean you have all the energy there. The somewhat category is the middle ground. So these are situations in which some energy is lost to the environment, but some energy is returned back to the objects, and so they do still bounce off. Okay? And I would argue that most collisions are like this. Okay? Most collisions, although I haven't done a survey of all the collisions that ever happened, but if you think about, let's say, driving on the highway, yes, you can have a horrible car accident where two cars merge to one. They crash and get all intertwined. But you can also have two cars trying to merge into the same lane. They bounce off, but clearly there's some energy dissipated to the environment. First of all, you heard it, so that's some energy that left as sound. Also, their side panels are dented, so obviously that all that deformation did not come back out. Some of it was permanent. So remember, just because you see a collision where two things do leave and part ways doesn't mean that the energy is all there. You could have a somewhat inelastic collision where there's a partial loss of not as much kinetic energy loss as you could have, but some. In fact, I would call the elastic collision kind of like the unicorn or the free lunch. It doesn't really exist. Okay? But let's say two things collide, two rubber balls collide, and maybe there's like 1% energy loss to environment. We might just say, 1%, who cares? It's close enough to elastic for our purposes. Okay? But if you're starting to lose 50, 60% of the energy, it's hard to justify that as elastic anymore, right? Okay, so these are in your, this is in your lab, where you get a little bit more comfortable with it. You'll try both of these. And you can see we have two subcategories. These are all momentum conserving, so elastic, somewhat inelastic, completely inelastic. They're all momentum conservation, all momentum conserving. The only difference is whether or not the energy of the system is all there. And I guess one thing that might be confusing, I'm equating the energy of the system entirely with kinetic energy. So for instance, I'm tracking whether the kinetic energy is the same at the beginning or the end. Well, the only time it goes into potential energy is during the collision. So usually I don't care about the details during the collision. And you might ask, where is the potential energy due to gravity? Well, if I'm doing this all on a horizontal surface, I might as well set it to 0, and it stays 0 for everything the whole time, right? So in these systems, when I talk about this, it's really, this is my action, because this is 0 all the time, and this is 0 except during the collision. So really, counting up mechanical energy is like counting up kinetic energy, basically. Okay, so let's move on to some different situations. Let's move on to the one from earlier, the two people pushing off each other on the ice. And again, my system is going to be the two people together. Is the momentum conserved? the momentum of those that two-person system conserved? Yes, it was, right? The force they exert on each other is internal, which is just fine. And we've done our best to isolate them from a net external force by making it be a horizontal frictionless surface. That's pretty much your dead giveaway. That's the best I can do to firmly announce to you that this is relatively isolated from the outside world, right? All right. How about the energy, mechanical energy? Is that conserved? No. What happens to it? Does it increase or decrease? It actually increases. In the previous example, it decreased. In the previous example, the inelastic collision, what became of that energy?